So we are talking about a kernel or local regression. I showed last time something about splines, which are one type of local regression, but the more general type is called kernel regression. And we motivated that by saying that sometimes we want to do regression globally, but sometimes we care about a local regression or trying to combine sources of information, continuous sources for continuous output from local areas. For example, if I want to compute a temperature in a very large room, maybe I don't care about the average temperature inside all the room, but I just care about the average. I have some sensors and I want to compute the temperature next to me, right? So that's one form of local regression. And we said we can do it by basically selecting some ball or some area around a specific point. And rather than using all the points, use just the points in this area. So that's definitely one way to do it. And I mentioned last time that this really resembles something we did in supervised classification, which was k-nearest neighbor, where we also selected. So this is the same idea, but now rather than doing it for classification, we can also do this for regression, right? And then basically we just compute some function of the values that we care about, right? So basically here, in general regression, we compute some weight of all the values. And when we do local regression, we may put the same weight on all of the points in our ball, right? So this is the weight that we put, and we just use those that are within yi is the value for that, and we just use the values for the points in the ball, right? So this is very close to a KNN classifier. So for that, what is the kernel function? The kernel function is basically the weight that we put on the point. And there could be different kernels. For example, this is called the boxcar kernel. Boxcar kernel basically puts a weight of 1 or 1 over n, depending on how you normalize it, but puts a weight of 1 on all points within some box or some circle, however you define it, some distance around you, and puts a weight of 0 on anything outside that, okay? So it's an indicator function. 1 means that you're in, 0 means that you're out. Everything that is in have the same weight, 1 or 1 over n, depending on how you want to assign it. And everything that is out has a different has a weight of 0. So that's definitely one way to do it, but that's not the only way to do local regression, because maybe we only care about things that are inside.
There's a quick question in the chat. Someone says, is KNN regression considered a special case of kernel regression?
So again, when you say KNN regression, the question is, how do you do the regression, right? So if even for KNN, so basically by definition, okay. So the short answer is yes. When you say KNN regression, basically you define the ball based on the k nearest neighbors. Okay, that's definitely one way to define it. Here, for example, the kernel that I mentioned is is different than KNN. Yeah, maybe I should have emphasized it. The idea is the same, that you just want to compute things in your ball. But unlike KNN, which basically defines balls of different sizes at different locations depending on the distribution of the points, in boxcar kernel, the size of the ball is fixed. Okay, we have some fixed ball defined by h. So that's a different kernel than KNN. KNN is another kernel, right? If you want to use KNN as a kernel, that's fine. But then the balls that you will get will be a function of the density in your area. Boxcar is different, it's fixed size, although of course the points change, but the size is fixed regardless of where the point is, okay? So both of these are possible kernels. And in fact, honestly, kernel is up to you completely to decide, as you will see. Both KNN and boxcar are actually defining 1 for things that are in and 0 for things that are out. That's not the only way to do it. When we do kernel, or when we look at continuous values, we can do something even better than that. And that will be, so right, this is the box kernel, or if you want to use it. But there are better ways of doing this, or different ways, I would say. And one of them is to use, rather than a box kernel, which basically is very sharp, right? Anything inside is 1, and anything outside is 0, which might not be the best option. Why? Because if you have things that are very close to the boundary.
Could you mute John? Since I gave you host privileges, I don't think he realized that he's unmuted.
The picture I sent?
I can.
How'd you?
You just hover over his picture, click the buttons in the top corner. Perfect. Thank you.
Sorry about that. So one problem, unlike KNN, where we said, look, we're looking at classification within a specific region, and we have really a discrete case value. In regression, we already mentioned it, that we want something that is continuous, right? We want functions that will not be very different when we move from when we slightly move. In classification, it's not a big deal because anyway, we move from 0 to 1. So at some stage, we will have to jump from 0 to 1. But regression, we don't need to jump. We can always be very gently sloping, right? And that's a problem if you use a boxcar kernel, if you think about it, right? Because let's say I'm using this is the size of my kernel, right? And these are the points. Right, so if you have a point here, it might only use, if you have a point here in the middle, it might only use this point. But when you slightly move it to here, it suddenly uses all of the points on the outside here as well. And that can make the jump can be very large, right? So that's dangerous because the boundary is very strict. Either a point is in or a point is out. That's okay, that's not, I'm not saying it's not something we can use it, but maybe that's not ideal. So another way of using kernels is to use something called a Gaussian kernel. A Gaussian kernel says that unlike boxcar, all the points are in. There is no point that is out. I'm taking into account all the points, which is similar to what we did in regression. But now we still want the local aspect. So what is the local aspect? The local aspect is the weight you put on the point. In boxcar, all the points have the same weight. In Gaussian, points have different weights based on how far they are from me. Okay. So you can do a kernel basically that basically for each point gives you a weight, and k basically represents the weight of that point. And then when you do the averaging, you average some points with a higher weight and some point with a lower weight. But if you really move a little bit, then the weight stays more or less the same for all the points because the distance of the other points to you doesn't change dramatically. Okay, so this is called Gaussian kernel, and there's lots of other kernels. In fact, as we will talk more about kernels when we'll discuss support vector machines, but basically speaking, you can use a lot of different things. And they are spatially adaptive, that doesn't really matter. And they can be used for the, right, so this is the, this, I don't know why. Yeah, for some reason, these are multiply. I don't know why it's, for some reason, I included this too much. Anyway, one thing to mention is the choice of the size of the bandwidth. Even if you're using a boxcar kernel, can have a big impact, as you can see on the results, right? So this is, some way to order the points and the predictions that you make. And you can see that, right, so things look much, so this is just some result based on distances. It doesn't really matter what the outcome is, what the input is, but the important thing is that you can see that we get, even for small changes in location, we can have a big difference in values, whereas things become much more smooth. Much more smooth when the size of the, or when the size of the number of points that are included increases. Of course, there is a danger because if you put too many points in, then basically all the points will have the same result. So there is this trade-off between being too smooth and not changing based on locality. So this is something that really depends on where you are. But this is, again, for boxcar kernel. As we said, one solution to this is to use a Gaussian kernel, which smoothes things much better because basically small changes do not affect a big deal. But it's still an issue to decide, even for Gaussian kernels, you need to decide on the width of the kernel, right? So for Gaussian kernels, the width of the kernel, right, is a function of the variance. Here I'm choosing the variance of 1, but of course you can choose another variance. So the mean is always going to be centered on the point that you're looking at. But the variance is something you have to choose. The bigger the variance, the bigger the impact that farther away points will have, the smaller the variance, the smaller. And again, there's no right, it's up to you. It depends on the domain. Okay. So this is basically it for local regression. And as I said, we will get back to kernels, or we'll discuss kernels in more detail when we talk about support vector machines. And there they will have slightly different meaning, but much more importance in terms of their use. Okay, so this is for linear regression. And again, we mentioned linear regression is linear because we multiply the output y is a linear function of the inputs, or transformation of the inputs, but fixed transformation of the inputs, right? So basically we do some transformation and then we take a linear combination of this transformation, which is parameterized by W, the parameters that we're interested in. And this is the output that we have. And this is why this is called linear regression, because it's a linear combination of the inputs or transformation of the inputs. But that's not the only regression we can do. We can do a regression where the output y is not a linear transformation, but some other transformation of the input. Maybe quadratic transformation of the input, maybe a combination of some quadratic W square or something, or maybe a exponential and so forth. One of the more useful types of regression that is not linear regression is something called logistic regression. And we'll talk about it in the next, or this is the topic of the next lecture. So let's, okay, good. So let's talk about logistic regression. So logistic regression is a regression, of course, a method, but we are now back to a classification. So we are, of course, in supervised learning, but we are back to classification. So we are back to classification. That means that the inputs are still the same inputs as we had before. They can be continuous, discrete, categorical, whatever. The output is going to be, for logistic regression, is going to be discrete. So 0 or 1, actually this can extend to a lot of classes. So 0, 1, 2, 3, and so forth, okay? And logistic regression is a discriminative classifier, okay? So in the same family as decision trees, support vector machines, which we haven't discussed, and so on. Okay. So let's, so I'm going to, of course, spend this lecture discussing logistic regression, but as you will see, logistic regression is a probabilistic classifier. Why is that important? Because when we will try to find the parameters for logistic regression, unlike when we did linear regression and we said we're going to use least square and maybe motivated by some probability, in logistic regression, it's going to be based on maximum likelihood estimation. You will see, we'll get to that in a few slides. But the reason I'm bringing this up is because this may, unlike, for example, decision tree, which is not probabilistic, or support vector machine, or even neural networks that are not probabilistic. So logistic regression does use probabilities. However, when I introduced it, I said that it's a discriminative classifier. Why don't I say that it's a generative classifier? We already said that probabilistic or generative is a function of probability. So why do we call logistic regression, even though it's using probability, a deterministic discriminative classifier? The reason is because unlike generative classifiers, right, logistic regression does not tell us how to compute P of X given Y. It tells us how to compute P of Y given X, which is the output, the class Y, but it doesn't tell us, so we cannot use it for the base part. So we are not right. In contrast, right, in naive Bayes, we explicitly try to compute P of X given Y. So that's why it's generative. But logistic regression, which still computes P of Y given X, is not generative. It's not trying to compute P of X given Y. Okay, that's just a point I wanted to make, because this sometimes confuses people that, you know, see or hear that I'm classifying, or I'm categorizing this as a discriminative classifier, but it's probabilistic. So, okay, it's probabilistic, but the probabilities, or there is no way to compute P of X given Y. Okay, but that's just a minor point. The major point is how we define the classifiers. What is the maximum likelihood estimation problem we are trying to solve, and when we solve it, what do we get? So for motivating that, let's say that we want to use regression ideas for classification. Okay, why? Because maybe, you know, maybe it's a good way to combine features, right? We saw already that for regression we get pretty good results when we combine features. So why not combine feature with some linear or other combination and try to get the classification that we want? Okay, and we already talked about linear regression, which is a great model for doing regression. So what if we wanted to use linear regression for classification? Okay, that's, maybe it sounds good, maybe not. But we can actually, or we can actually at least set up the problem of linear regression for classification in the following way. So of course, in classification, unlike in regression, we're only going to have two values. Let's say two classes for now. Okay, this can be extended to more, but let's say two classes. In classification, we're only going to have two classes. So some points, and again, I'm assuming now that X is univariate, although that will be true for other things. So for some X's, we are going to have one, class minus one. And for some X's, we are going to have a class of a class of one, okay? Now, if you want to find the linear regression in this case, you basically find a line, right? What is a linear regression? It's this line that connects X and Y, right? So given X, it will give you Y. And let's say we want to find a line, right? That if WTX, so W is the parameter, in this case, W is just one value. If WX is greater than 0, basically, if you're on one side of the line, you will be positive, we'll say class 1. And if you're on the other side of the line, we will say that you're negative, class minus 1. Is there any line that would work for this set of points? Anybody can think of a line that would work for this set? I mean, can we find such line for this set of points that will lead to optimal classification? Basically, a line means that, right? If we have a line, then Y equals some function of X, right? I mean, or with a bias, because it doesn't go through 0, 0. So Y equals W0 plus W1X. That's basically the definition of a line, right? That's by definition a line. So let's say we want to find a line for this problem. Can you suggest a line? Can anybody suggest a line that will solve this problem perfectly? Let's see. So, yeah, horizontal at 0, again, depends on what you call 0, but I guess, right. So the answer is, of course, as people said, yes. And in fact, there's multiple lines, at least for the data that I gave you, right? So for example, if we put a line here, wherever this is, that would be perfect. Maybe I can plot it, but there are other lines as well, obviously, that you can find. Right, so we have this, and we have some points here, and some points here. And we can put a line here, or we can put a line here. I mean, a lot of lines will separate these points pretty well. Or line here, and again, I mean, maybe the straight line is the best, right? Because we assume that there is a straight, but given the points, all of these lines would work. For the training data, all of these lines would work. Okay, so the reason why I'm bringing this is because given this definition, right, there is a solution for the linear regression problem that, if we look at classification, will work optimally, right? If I put this line, it will classify, again, we don't know about the test data, but all the training data will be classified perfectly if we choose this line, right? That's by definition a line, and we can find this line. Okay, so now let's say that we now learn a linear regression model, okay? Using this definition, basically. What is this definition? So the linear regression model gets X's, which are these values here. It gets the Y's that are these values here. And it gives us a line, because we said we want W0 plus W1X. What line will the linear regression classifier give us? Anybody can predict, can say? Right, so we want to predict Y from X, yeah. I mean, of course, from our perspective, Y is the class, and X is the input. So what line would the classifier give us? Would it give us the straight line? Would it give us a little bit slightly different line? What type of what do you think would be the actual line that the classifier will give us? If we plot it, anybody can guess? Exactly. So yeah, Yeah. So the answer is going to be actually a very bad line for classification. So if we go back to our drawing, the line that we'll get from solving the linear regression as we defined it before, right? The least square linear regression problem, that's the way we defined, will be something like this. Why is this the case? Because this line is closest in terms of the projection of the points to the line, right? Each of these points is very close. If you put the line here, then the point on the right is very far from the line, and also the point from the left. So this is not a good way to minimize the squared error. The error is going to be very large. On the other hand, if we go like this, it's great. It's a great line in terms of the least square. Unfortunately, if that's the line, then the classifier is going to make mistakes on these two here and on these two here. Well, depending on how you define it, right? Even though we can get a perfect line, the line we get from solving the linear regression problem, as we defined it, is not going to be a good line for classification. And again, that may or may not be surprising, but that's the reason is because we are not, we didn't intend linear regression to solve classification problem. It was meant to solve a regression problem. In regression problem, we want to get the points as close to the line as possible. We don't care about whether it's plus more than the line or less. We just want the least square. So that's not going to work. But anyway, the reason we did this exercise is to show that on the one hand, regression can maybe be used, but on the other hand, the way we defined it is not good. So what can we do? What we can do is change the target function that we are trying to optimize. Rather than optimize least square, which wouldn't work well for classification, maybe we should optimize another target function. We still want to use regression, but optimize another. Okay, so this is the optimal regression model, which is not good for us. So for that, I'm going to introduce a new function, and then I'm going to say how we can use it for regression. The function that we'll use is called the sigmoid function, and it's a function of one value h. Of course, h can be computed as h could be equal to some other thing, but given the value h, this is the function. So you can see a few things about this function. The value is always between 0 and 1. Okay, so when h approaches minus infinity, this will be 0, and when h approaches infinity, this will be 1. But even for very small values of h, it's already very, very close to 0, or minus will be very close to 1. Okay, and there is some slope here, which is this slope here. Of course, you can control the slope by looking at, if I do e to the minus 100h, then the slope will be much steeper because any h will be multiplied by 100. Or if I do e to the minus 0.0001h, the slope will be much smoother, right? Because every h will be, okay? So you can play, by playing with the values of h, you can actually play with the slope, but there is some slope here between, so it's not going straight up, there is some slope, but the slope, the scale of the slope is a function basically of h, right? So if you change if you change some value that multiplies h, it will change the slope. Okay, so this is a function. Again, the important thing for us is that it's always between 0 and 1, which immediately brings the idea of using it for probabilities. So we can, we know probabilities are always between 0 and 1 as well. And we need to show that in it. So using that, an idea we can use, or one possible way to use this, is to define the probability of a class using a sigmoid function. So we have, and again, use that as the target function, and we will see in the next slide why this might be useful. But for now, we can just have this definition that we will set P of y equals 0, the probability that y equals 0, condition on x, and theta is the parameters, but condition on x, the input, as 1 over 1 plus EWTX. So what did we do here? WTX is a regression, right? W is the parameters, X is the inputs, and this is the H that we have here. I drop the minus. Why do I drop the minus? Because I can just plug in the minus in the W's, right? So W can be plus, minus. So I don't really need the minus that I have here. If I really want a minus, I can put it in the W. So W are unrestricted, okay? And some of them will be minus some. But anyway, once I define that, then WTX will control where the prediction is going to be along this curve here, right? If I think this should be class 0, then I want the value of WTX to be very, very low and negative, right? I want it to be close to this, and this will be basically 0, because if WTX is negative, then the sigmoid function is 0. If WTX is very high, or if I'm in class 1, then I want WTX to be very high. In that case, this will be close to 1, and we can put it as and it might get very close to 1. I mean, the reason why we're doing this is because this has to sum to 1 as a probability, right? The probability of class 1 plus. So we know that the values have to be always between 0 and that's one requirement for probability. The other requirement is that if we have 2 independent events, or if the domain contains 2 independent events, then the sum of these 2 events has to be 1. So that's what we are requiring here. But the important thing again is that by controlling the value of WTX, and which we get to set, we can set the probability of a specific sample to be either 0 or 1. That's the part we want to learn. The other thing I want to mention is that this still is a regression problem. So we end up with W multiplying X, but it's not a linear regression anymore because everything now is in the exponent of some function. So this is not a linear regression because the Y, the output, which we treat as probability, but it doesn't matter, right? It's a continuous value, so we can still do regression, although we treat it as a probability of a class. But why the output is a combination, but it's not a linear combination anymore of the inputs. It's some function of the inputs, which is not linear, right? Because it's 1 over e to the power. So it's still regression. W is still multiplying X, but the output is not direct function of that, but rather of the exponent of 1 over the exponent. Okay, so we are in the regression space. We are talking about probabilities, and we get a probability. Okay, so this is just a definition. The important thing about this definition is first, it provides a probability for the 2 classes, and second, the probability is valid. So the values are always between 0 and 1, and the domain, or if we look at some of the events in the domain, they have to sum to 1 by definition. Okay, so that's at least, it's a valid probabilistic assignment. As I said, this is not a linear regression. Okay, another thing we said in the beginning, but now you can see, is that we don't really know how to do X given Y in this model. We don't even define what it means to be, or we don't define a distribution for X in class 1 and a distribution for X in class 2. We don't know how to compute it. We don't, unlike in, for example, naive Bayes. The only thing we care about is the probability of Y given X. We don't know how to do the other side. Right? We don't deal with that. We only care about this side, the probability of Y. So this is a discriminative function. It's not a generative function because we cannot generate X if we knew Y, because we never defined any probability of X given Y. We only defined the probability of Y. That's it. Okay. So now, right, let's look at the differences between what we said before. The nice thing about logistic regression function is that it can set this boundary, and of course, X can be any dimension. It doesn't have to be a univariate variable. It could be multivariate and so forth. But it can set the probability of any input to be between 0 and 1. And the boundary that it computes, right, is the boundary between the points. So the goal of the function, unlike linear regression, is not to be very close to each point. It's to get the actual class correct, because we want to maximize, or we want the probability of Y to be as close as possible to the actual Y. So if Y is 0, we want the probability of Y equals 0 to be close to 0. And if Y is 1, we want the probability of Y equals 1 to be close to 1. Another important thing is that we control the shape of the boundary here. So the boundary is always going to be something like this. But if we are very, very confident in our model, we can have very, very large W values that for any X will either push it very, very much to the left or very, very much to the right. So we can have a very tight slope, right? When X changes even a little, it can move from being minus negative to minus positive, okay? So on the other hand, if we are not very confident in the center, we can have the slope be much smoother, right? Much less steep. And then we can have things that are 0.4, 0.3, depending on, we are not very confident about that. So that's something we control by changing W's. Okay, so that's another advantage of logistic regression. Okay, so this is something we defined as a function. We said that it's a valid probabilistic model, but we didn't say how we are going to actually find the parameters that will lead to the best answer, because now we want to find parameters that for samples in class 0 will say the probability of 0 is very high, and for samples in class 1 will say the probability on class 1 is very high. Right? That's the question that we would like to answer. How do we answer such question? How do we find such parameter? The answer is, because this is a probabilistic, even if it's not generative model, it's still a probabilistic model. As we discussed in the first or second lecture, the way we do it is using maximum likelihood estimation. Okay, so once we have a probabilistic model, in this case, for classification, but it doesn't matter. Once we have a probabilistic model, we can use maximum likelihood estimation in order to find, we can also use map, but but we don't want to make any assumptions. So in this case, we just use maximum likelihood estimation using the training data in order to find the parameters. Okay. So the goal of the next part is basically, or the goal of the rest, I guess, or part of the rest of the lecture, is actually to find the values of the parameters that will maximize the likelihood. Okay, how do we define the likelihood of the data given the model? Right, so this is again the definition that we had for the logistic regression function, right? We said the probability of y given 0 is 1 over 1 plus e to the power of x. I'm going to use a shorthand notation for that, and I will call it gxw, and this is 1 minus gxw, because this is 1 minus the probability of 1 is 1 minus the probability of 0. So I can write it this way as well, right? I mean, you can see that these two sum to 1. So this is just a notational issue. I didn't do anything here, okay? But I will use that in the maximum likelihood estimation. So this is the maximum likelihood estimation. And I'm using a slight, I don't want to say a trick, but a shorthand notation for that. Basically, the maximum likelihood estimation is the probability, right, of the data given the model. What is the data? The data is basically the label that we assign to each of the samples. That's the input, and the model is the prediction based on X, right? So for each sample that is in class 1, we want to use the probability of class 1 that the model gives them, right? Because that's the probability that's the right solution we need to give for a sample of class 1. So if I have a sample of class 1, then I'm using the prediction for class 1, which is 1 minus gxw, and I'm taking that to the power of yi, right? Which is basically 1. So if yi is class 1, then I'm going to use this part here. So if I is from class 1, I'm going to use this part here. If I is class 0, then I want to use the probability for class 0, because that's the right solution that's what I want to maximize. That's the probability I want to maximize, and which is dxiw. In that case, I take that to the power of 1 minus I. So if I get a sample of class 1, I'm going to use this probability. And if I get a sample of class 0, I'm going to use this probability, and I take the product of all of them. This is just a way to write it down. I could have written it as pi over all samples of class 1 this, and then pi over times pi of over all samples of class 1 of class 0 of this. But this is just a way to write it together, okay? But the important thing is this is the likelihood of the data given the model, right? The probability that we find the right class divided by the two classes. Okay, that's the definition, and again, a shortened way of writing it, but other than that, it's correct. And now we want to find, so this is the likelihood of the data given the model, and now we want to find the maximum value we want to find the value of the parameters W that maximizes this likelihood. That's the goal. What's the first?
If someone has a quick question, someone says MLA should be the probability of data given W, but here it's the probability of Y given X and W.
So the data, right? So X we don't have, right? So in this case, right, we don't have, right? I mean, you can, okay, good. Let me, yeah, so. So, right, we are computing P of X, Y given the model, right? That's what people said. And this is basically, right, P of Y given times P of X given theta, right? This is the chain rule. Everybody is okay with that? I only focused on this because basically X doesn't, or we don't have any model for generating X. So we don't even care about generative X. So this will basically, whatever values we assign to theta, this will stay the same. So we don't, I mean, the maximization function doesn't care about this part. It only cares about Y given X. Okay, so you're right. I mean, we are only maximizing the part of Y given X because the probability of X and theta, of X given theta is not defined or something that we don't care about, or will be the same basically for all parameters that we use. Okay, good. So that's a good point, but in this case, that's the main function. Okay, good. Thank you for the question. So let's, oh, I actually wanted to use. So yeah, so what's the first thing we should do in order so what's the first thing we should do to find the maximum likelihood estimation? Right, so we want to find maximum likelihood estimation. What's the first thing we would be good to do for this data? You've all done the problem set, so you should now be clearly. Right, so we write down the likelihood, we wrote it down, of course, and now what's next? Now we want to find the, yeah. So the first thing, even before we take the derivative, which we'll have to do, is the log, right? Because we have these exponents here, it makes sense that taking the log would be a nice idea, which is true, as most of you found out. Okay, so the first step is rather than compute, so this is the likelihood of the data, right? The likelihood of the data of Y given XW. And the first part is really to take the log of the data. So let's do that. So this is LL is the log likelihood. We are not doing any derivation or anything. We're just taking the log. Right, so if you take the log, obviously all the y's go here. This becomes the log. It's log of this function here. Yeah, I'm not going to derive this. But basically what I did is right, so this one is just yi ln, I mean, I'm taking the log of base E in this case, right? Because we have E in the exponent, so we are using log E rather than log 2. But this is the first, right? This is just taking the log and moving the exponents out. And then, right, and then we basically sum the values that have yi. So this one is 1 minus this, so this becomes a ratio, right, or a fraction of 1 of this over this, and this is the part from 1, and then if you actually put the value, so right, if you now substitute g of xw to what it really is, you actually get these two values. Okay, so this comes out of actually putting the values here. Okay, so again, this was 1 over this, so this minus 1 went here, the denominator went up to the numerator. That's exactly that. That's not a big problem. Anyway, this is simple algebra. So once we do this, we get to this function here, which is, you know, some sum over yi, wt, xi, doesn't matter. And now we have the log likelihood of the data. So the next step, of course, is to take the derivative with respect to the parameters, right? So now we have the log likelihood. We made it as simple as possible. And the next step is to take the derivative. And we take the derivative with respect to the parameter. In this case, the parameter is, of course, W. Or let's take the partial derivative with respect to one of the W's. It doesn't matter. Let's say Wj. Now, if you want to take the derivative with respect to W for this function, because it's a sum, basically, so this is very easy, right? I mean, the derivative is just W. In this case, if you take the derivative of wj, it's just xji times yi, because everything else falls apart if you take it with respect to one of the parameters. The derivative here is slightly more involved, but not much more, right? If you have a derivative of a function, then you take the derivative of the function. For this case, it's ln, it's 1 over the value here times the internal derivative, which is basically e to the power of wtxi times the internal derivative, which is xij. And basically this becomes, so you basically, you get this part for the first, and this is the part you get for the second. Okay, and you can do this yourself, but basically the derivative of a ln is 1 over the value you have in the ln times the internal derivative. And the only thing you have to be careful is the internal derivative here is e wtxi times the internal derivative on the exponent of x of wt, which is xij. So that's where you get the xij. Other than that, this is pretty simple algebra. Okay, so this is the derivative that we get, and again here I write it in the notations that we used of 1 minus g, which is basically right here. Basically, this is just e to the power of wtx 1 over this. But more importantly, we already said that 1 minus gxiw is the probability of y equals 1. Okay. So this is what we end up at the end, which is nice. I mean, it's nice because it shows you, right? And then we want to, so what's the next step that we need to do? So we took the derivative. The next step is to equate it to 0, right? And when we equate it to 0, this will lead to the best W. Why is that the case? Because when this equals 0, what happens? If yi is 1, right? In order for this to be 0, then the probability that y equals 1 has to be 1. Otherwise, it wouldn't be 0, assuming that xi is some arbitrary value. So for this to be 0, when yi is 1, this should be 1. And when yi is 0, this should be 0. Otherwise, it will. So that actually shows you that just, I mean, we don't need that because we did the derivation, but you can see from the derivation that if we find a W that basically maximize right, well, yeah, I guess that minimizes the error here, you actually get the maximum, or you can get the maximum. Otherwise, you can get like the sign, because this will be basically a minus value. It's not always true, depending on the value of xi, but generally speaking, this is the error that you get for the function, right? And when this comes close to, or when this comes close to, or when this is, in order for this to be 0, or the other way around, if W is such that we get all the values perfectly, then this is 0. And when this is 0, this is the optimal we can get. Obviously, maybe we can't get to 0 all the time, but at least we can try. We can't always get that this part will be 0. So maybe this part sometimes will not be 0, and this will make it like the summation will make it 0. But anyway, if we do have the perfect solution, this will be 0 by definition. But that's just a minor point to show you, but it doesn't matter. It comes from the end. Okay, good. So now we did this regression. We took the derivative. Everything is good. But we still have a challenge, right? We still need to find the value of W. So how do we find the value of W here? Well, we usually just separate things. We move this to one side, we move this to the other side, we divide, we do this. Unfortunately, this is not going to work in this case because W is in the exponent, and this, what this is really is this part here. You can play with it, you can try, but a lot of people have tried for several decades, and there is just no closed form solution for this. Okay, so there is no way to get W out of this equation even after you equate it to 0. Just a fact. I mean, again, I'm not going to try, and you can try if you want and if you have time, but the consensus is that you cannot get W out of this equation. So what do? We still want to find the value of W. What do? We are going to introduce now a method that is very important in this class. And we already introduced one general important function, which is called MLE, which we used already several times and we'll use again. The function that, the method that I'm going to introduce next is similar to MLE, a general purpose function. We are going to introduce it now for logistic regression, but it's going to be something you will use a lot in neural networks and in other cases. Okay, and this is something that is called gradient descent or gradient ascent for this, because we are maximizing the likelihood. Gradient descent is normalization function. So what is gradient ascent and why do we want to use it? So again, remember, we have this issue that we want to find W, but we don't know, or we cannot separate W out of the other components. So how can we still find W? The answer is we can improve on W rather than find a closed form solution for W. We can iteratively try to improve on the W's that we get. How do we improve on W? How do we, let's say we started with some W and we want to find a better W. How do we do that? So one way, there are several ways of doing it. One of the most popular ways is something called gradient descent. Gradient descent means that you need to take the derivative with respect to W, which we already did, and then look at that derivative to decide how to change W for the next iteration. It's not a way to find the best W. It's not like if you did it, you will find the best W. The only thing that it tells you is that you will move slightly closer to the optimal W. And if you repeat it enough times, you will get pretty close to the optimal W, or maybe you'll get exactly to the optimal W if you can get it. What's the idea? The idea is that depending on the shape of the function, right? In our case, we want to find the maximum likelihood. So the shape of the function, if it's convex, it looks something like this. So it's going up, it's up to some value of W, and then it's going down. And this is true, by the way, for one value W, but it's also true for individual W. So WI, WI plus 1, W1, W2, W3. Okay, so we have this type of slope where there is one optimal value, and before and after it, the function, which is what we want to maximize, right? The function that we are maximizing is slightly less than the maximum value. Okay, so this is the function that we want to maximize. Now, if we look at the slope here, the slope of the function that we want to maximize is the derivative, right? That, by definition, derivatives are the slope of the function. So let's see what's the relationship between the change in W and the slope. If the slope is positive, so if we have to, if we go from here to here, we see a positive slope, basically we increase, right? If the slope is positive, we increase, delta Z increases the value of the function. That means that we are in the range where we would like to increase W. So if W increases, if we are here, the slope is positive. It means that if we increase W, we'll go closer to the max value. If we are here, the slope is negative, right? Because once we move in this direction, the value reduces. So the slope is negative. That means that we would like to decrease W. Okay, so if the close is positive, we would like to increase W. If the slope is negative, we would like to decrease W. We don't know by how much because we don't really know. If we knew this function, right? If we knew how this function looked, we would just go to the max and take it. We don't know how the function looks, but we can say more or less where we are on the function, not with respect to the peak, but with respect to are we going up or are we going down. If we are going up, we want to continue to go up until we reach the peak. If we are going down, we want to reverse that and start going back to the other direction. Okay, so what we have here is something called gradient ascent. So we look at the gradient, we look at the derivative. Based on the derivative, we decide on our next move, but we don't know how big the move should be because we don't know the function. The only thing we know is the direction of the move. So if the slope is positive, we increase W a little bit because we don't want to jump over the peak. If the slope is negative, we decrease W again a little bit because we don't want to jump to the other side. That's the idea of gradient descent. Gradient descent, compute the slope. Based on the slope and the function, in this case maximization, change the W a little bit in the direction of the slope. Gradient descent is the opposite. Gradient descent means usually for minimization functions, and in that case, you change it in the opposite direction to the slope. But in our case, we are trying to maximize a function, so we're going with the direction of the slope. Okay, so this is gradient descent, right, where we have a minimization function. And when we have a minimization, and the reason why I'm mentioning it is because you will run, I mean, most people actually use gradient descent rather than gradient ascent, because in many cases, or most cases, this is used for minimization functions. And in that case, when we have a minimization function, like, you know, some least squares or something, then the goal is to go in the other direction, right? So when the slope is positive, right here, you want to decrease W because here the function goes up, but you want it to go down. So you want to decrease W. And when the slope is negative, which is here, right? So the function goes down, you want to increase W because your goal is to go to the negative side. Okay, so this is, again, just difference between gradient descent and gradient ascent. The important thing is not so much the name. The important thing is the function, the method. The method is iterative. You compute this gradient iteratively, and I will show you in a second how you do it. You compute this gradient iteratively, and once you computed them, you move in the direction of the gradient. The quantity that you move in the direction is not part of the algorithm. It's up to you to decide, and I will show you in a second that this can have a huge difference on how fast you get to the optimal solution. And again, the worry is, on the one hand, you don't want to jump from one side to the other, right? Because if you miss the peak, if you increase W too much and you go to the other side, then you have to go back and forth, sometimes too much. On the other hand, if you go too slowly, you will get to the peak, but maybe it will take you 2 years, which you don't. So there is this trade-off between a size that is big enough to make a difference and small enough to not jump over to the other side. And I will show you, there's no way to actually, it's hard to find the right solution, but this is something you can try. So this is the way we do gradient ascent, basically. So we compute the derivative for W, right, which is this value here. This is the derivative for W that we computed, right? This is the derivative. So before, I mean, that's what, when we took 6, this is the log likelihood, but it doesn't matter. When we find the derivative, this is what we found. And now we start with some guess for Wj, and we change Wj based on the direction of this, right? So this is positive times some epsilon, times some very small value, okay? So we are not going to use this value that we computed because we are multiplying it by a relatively small value, but we will use basically the direction. If this is, so epsilon is always positive. If this is positive, W will increase. If this is negative, W will increase. So this is the basic idea of logistic regression with a gradient descent, right? So we start with an epsilon, which is what we call the learning rate. We guess W. Okay, so we guess a value. We have to start with a guess. You can guess W as 0, right? So just guess all the values of W as 0. Or you can guess 1 or whatever you want. And now we start iterating. First, we compute the derivative with respect. So once we have W, we can compute this function, right? This is a function of W, the derivative. Once we know W, we can compute the value of this function because this is a function of W. Y and Xi are given to us. The only thing that is missing is W. We guess W, so we can use it. So now we computed this. Once we compute this, we can see if it's positive or negative, or we actually have the value. We multiply it by epsilon, and we increase J. Okay, and now we test the likelihood function using W, and we compare it to the previous. So we have a new W function, right, which we computed, and now we ask whether there is an improvement to the overall likelihood or not. If we are moving slowly up, then there should be an improvement, right, because now the W is getting better and better and better and better. So if we are moving slowly up, we will find an improvement until at some stage we go over the top and we start decreasing, then we stop because we reach the peak. If we move too fast, then we can have actually a decrease, not because we moved up, but because we just jumped too much. So it's very important that epsilon is very small. And again, I will show you an example. Okay, but once we do that, we basically stop when these things converges. Converges means that we cannot improve the likelihood function. One point I want to make is that this is the general the general gradient descent algorithm. The challenge with that, or not the challenge, but one thing you should realize is that each iteration you should basically sum over all the samples. So this can take a long time, especially if you have a lot of samples. So and of course this is done separately for each of the WJs. So you need to do it for all the J's, and for each J you need to sample you need to go over the samples. So this is called gradient descent. There is another method that speeds this up that is called stochastic gradient descent. And in stochastic gradient descent, which I think you will use in the problem set, rather than computing this for all the samples, you just do it for one sample. Okay, so the equation remains the same, but rather than summing up on all the samples, you just pick one sample at random and do it again. And the idea is that if you do it enough times, you basically approximate the real gradient descent. In neural networks, you will see another solution, which is called batch gradient descent, which rather than do it on one or everything, does it on a subset, which is called a batch. Okay, all of these things are just approximation to what I'm showing you here. And the reason why we need this approximation is because we want to speed up. This can take a very, very long time. If you have 1 million images and you need to do it each iteration, you can think how long this takes. But this is the actual gradient descent algorithm. Okay, just for. Okay, good. So if that's clear, let me show you an example of gradient descent. And the example I'm going to show you, just because it's easier, is gradient descent applied to linear regression. So that's may or may not. Let me stop showing for a second. So that may or may not sound like a reasonable thing to do, because we already said that we can find the W for linear regression in one shot. The problem with the problem when we do it in one shot is that it can take a very long time, because, as we said, we need to convert a cubic matrix, or we need to inverse a matrix, and that could be cubic in the size of the, in our case, in the size of the features. So if we have a lot of pixels, if we have a lot of features, maybe we cannot solve, or we don't want to solve linear regression in closed form. It turns out that you can use gradient descent for linear regression as well. Okay, even though we're doing linear regression, you can do it with gradient descent, and you will get to the same solution, but you will be, right? So again, in linear regression, it's a minimization problem, unlike an optimization. So we're going to use descent rather than ascent, but other than that, we can do the same thing. And we are guaranteed, because it's a convex problem, we are guaranteed that if we move slowly, we will get to the optimal solution, which will be the same as the closed form solution. So we can use you can use gradient descent for linear regression. It's something that we often do for speed, but also in neural networks, for example, which sometimes combine linear regression and logistic regression and other functions. It might be better to use the same optimization method for all of them. So linear regression, of course, so logistic regression, we can only use gradient descent. So it's good to use gradient descent for linear regression as well. So sometimes we use it, even if we can solve it in closed form, sometimes for the ease or for the consistency, we use gradient descent. Okay, just again, just a motivation, but the example that I'm showing you is for linear regression. Okay, so I don't know if you can see my screen. 1 second, let me share it. So I'm showing you a quick MATLAB implementation of gradient descent. So we'll start by setting up the problem. So basically, I'm setting up values for x between 0 and 20. So this is a linear regression problem. So x is the input, y is the output, and I want to introduce some noise. So I'm going to set some random noise. Let's say with mean 0, this is normal distributed with mean 0 and subdivision. Okay, and now I'm setting y to be 2 times x, okay? So y equals, it's a linear regression problem, so the w that we're looking for is 2. Okay, so now we have the inputs x, we have the outputs y, and our goal is to find the w, which is 2, okay? So let's do that using gradient descent. And in this case, just to show you, x and y are the values that we put as input. 0 is the original prediction, or the initial prediction for w, right? In gradient descent, we need to have an initial prediction for w. It can be 0, I can change it later. 2 is the real w, and I'm just using, I mean, the algorithm is not using it, but it's good for first. And this is the learning rate. And as you will see, this has a big impact. So if we use a different learning rate, it will either be faster or slower, or it can completely diverge. Okay, so let's see what happens when we do this. Why is it so slow? Not sure why it's so slow. Anyway, so this is the value. This is the what you get for, if you use the real w, the real w, which is 2, and this is the linear regression gradient descent approach. So red is the value of w that it predicts at each iteration. You can see that it gets closer and closer to the real 1. It started with 0, and it's getting closer and closer to the actual 1. Why is it taking so long? 1 second. Okay. So now what happens when we change the initial prediction? Let's say we start with -10. So you can see that it starts much worse, but it's still getting pretty close to the right solution. Even if we started worse, it's moving in the right direction, and eventually it will get to the right solution. Even if we start very bad w, as long as it doesn't jump from plus to minus, it's going to get, oh, I stopped it after 10 iterations, but if I let it go, it would have gotten to the right solution. Okay, so this is for this. What happens when we change the learning rate, right? So we started with 0.05. If I change it to a lower learning rate, you can see that it's moving in the right direction, but it's moving very, very slowly. So this starts at 0.003. It's not moving. Okay, so now it's moving, but it's moving very, very slowly, right? If we had a bigger one, it would have moved bigger. So it's moving, but it's moving pretty slowly to the right direction. I'm stopping it after 10 iterations, so it will never get there. If I make the learning rates faster, let's say this, then it will move very fast, but sometimes in this case, it just overshoots it and it goes back and forth from side to side. So that's also not good. So there is some learning rates that are optimal because on the one hand, they move fast enough, but they don't overshoot. And some learning rates are, so this one should be, I think, fine. right? You can see this moves pretty quickly around the point and gets there very quickly to the right solution. By the way, the optimal solution, even though it's 2, the optimal solution for this case is 2.02, which is even better than 2. If you look at the error for 2 is 18, and the error for the solution that we found is 16 points. So basically, it gets you a better error, again, because this fits some of the noise that we have. Okay, good. So this is an example of gradient descent. The key points are that if you change the learning rate, you will do faster or slower depending on the learning rate. Unfortunately, you don't want to do too fast, because if you do too fast, then your learning rate, or then you basically jump back and forth and you will never converge. Okay, good. Yeah, so I changed. Okay, good. So this is an example. Let me, okay, so now let's do a Piazza poll, okay? I mean, it's a good time to review some of the material. So I'm going to release the poll on logistic regression. As before, right, there is no grading or anything, but yeah. Yeah, so please take a look at the poll and do the 2 questions that I released. Yeah, so the second question obviously is more involved. You might need to think a little bit about it. Of course, we saw a similar question for KNN and decision trees. In fact, the same question. So as I said, this is a nice question because it's really maybe gets you to think about different models and the impact that different things have on them. Okay, so a few more seconds. Yeah, try to get an. As I said, this is not trivial question. So if you don't get it right, it's not a huge. I mean, I'm talking about the second one. And the first one should be easier. Okay.
If someone had a quick question, they said they're wondering if the parameters of the linear regression in question 2 will be estimated as the X matrix now has multiple collinearity.
Okay, so let's assume we use gradient descent, if that's right. I mean, we can do gradient descent. Okay, so let me start with the first question, which hopefully everybody had time to complete. So the first question, I asked you something pretty basic about logistic regression that I actually mentioned in my slides, and that is if we have a probability for class 1 and class 2, what's the relationship between them? And the answer is, because this is a probability function, and we assume that the probability the logistic regression calculates is P of y given x, and the domain can only have 2 values. For now, we assume that it's 2 classes, 0 and 1. Then the sum of the probabilities for the 2 events, which are disjoint, has to be 1. So if the probability for one class is 0.7, the probability for the other class has to be 0.3. Okay, so most of you, the vast majority got it correct. The second question is more interesting and fun because we already asked this question about k-nearest neighbor and decision trees. And in that, not decision trees, we actually did not ask it about decision trees, although I should have asked it about decision trees. You can think about it for decision trees. But I did ask it for k-nearest neighbor and naive Bayes. And for both of them, the answer was that the classifier will change. Okay? So now we're asking the same question. Basically, I'm duplicating the value of the first input of the first feature in each input, and I'm asking how is this going to affect the classifiers. Now, a key point in this question is that the classifiers that we get are optimal. Basically, we have a lot of data, enough for us to find the optimal classification or regression model. Okay, so there's no better answer than the answer that we already have from the data that we have. Okay, so what would happen to linear regression and what would happen to logistic regression? So we know, and this is true for both of them, but let's start with linear regression. We know that there is W1 that is optimal for X1, right? So linear regression, Y equals W1 plus W2X2, let's say for individual samples. right? That's that. We know that there is W1 that is optimal for X1. Now we split X1 to X11 and X12, right? That's the only difference. Everything else stays the same. Is there a W that will be optimal for these two? What W will be optimal for these two? For example, W1 over 2 plus W1 over 2. Or you can think of other combinations, right? But any combination where X11 plus X12 time, or basically, right? If we have, let's say, any combination in which, let's say we put W11 X11 plus W12 X12, and any combination where W11 is equal to W1 would lead to the same solution as the original solution, right? So it's not impossible. In fact, it's easy for us to get to the same solution. What do we know? We know that the previous solution is the optimal. We cannot do better than that. So the new solution must have the W's obey this function here. They must have W1 equals W1 plus 1 plus. Otherwise, right, W1 will be different. If W1 will be different, the solution will be different from the previous one, but it's not going to be optimal. Now, of course, if we cannot get to the optimal, that's something else. But we know we can get to the optimal with these samples. So it must be that the new solution will have the same value. And so the answer is that linear regression is not going to change. What about logistic regression? Same thing, right? If we look at e to the power of wx, right? If I set w11 plus w12 to be w1, then e to the power of wx, when I have x11 and x12, will still be the same. And we know that the previous method, or the previous w's, led us to the perfect classification. We cannot do better classification. In that case, the perfect classification will be when W1 equals W11 plus W12. And in that case, any point that we will get the same prediction as before, right? Because the W times X, the overall value will still be the same. Okay, so this is slightly very different, I would say, from what we had for k-nearest neighbors and naive Bayes, where we did have a difference. In this case, again, this is only true, again, it's only true based on the caveat that I wrote that we have the optimal classifier. If the classifier is not optimal, there will be a difference because we are introducing a new value here. It could change, at least for logistic regression. I'm not sure about linear regression. Actually, linear regression, it shouldn't change because we basically get the same. But for logistic regression, I think it can change. But definitely, yeah, I remember this came up. So for linear regression, yeah, that's actually an interesting question that I keep asking myself. So clearly, when the classifier is optimal, there's not going to be change. When the classifier is not optimal, for linear regression, there's not going to be change. For logistic regression, I'm not sure, actually. I have to think about it. I don't know if anybody has a good argument why it could or could not change, because it might actually not change even if it's not optimal. But anyway, in this case, if it's optimal, it's definitely not going to change. Okay, so let's go back to our problem, or to our class. And I want to mention a few more things about logistic regression before we finish. So we already talked about how to find the values for logistic regression, which is the most important thing, but there are other ways of doing it. So far, we basically solved the MLE version of logistic regression. But there is also something called regularization, which is much more similar to the map estimate than to MLE. What is this regularization thing that you will actually work on in the problem set? Regularization is a way to limit the value we assign to parameters. Why do we want to limit the values we assign to parameters? Because sometimes we may think that there is not enough data to accurately predict the values of the parameters. And I already showed you in the polynomial case that if we give too many parameters, we are going to fit the data very well, but we will end up overfitting. And in fact, in polynomial regression, if you look at it, you will see that what happens in practice is that if you allow for a much higher polynomial, you will get W's that are very, very large because they have to go very high and then come down. And then. So it turns out that a good way to reduce the overfitting issues or to reduce the impact of overfitting is to limit the values that the W's can take. For example, one way to regularize or to limit this set of values is to say that we have some prior on the W's, right? This is a probabilistic function. If we have a prior, this becomes, rather than an MLE, it becomes a map estimate. What is a potential prior? The potential prior is that most features are not important. That's the motivation. Most features are not important for data. Only relatively few features are important, right? So if most features are not important, what should be the W for these features? It should be 0. We shouldn't take them into account, right? So if that's the prior we have, we can set the probability of W to be 0, or sorry, to be a Gaussian with mean 0 and some standard deviation. The standard deviations means that some features are important, so we allow them to take values, even very large values, although they will be penalized. But most features should be 0. If that's the case, then we assume that Wj is distributed with means that is 0, because we assume most of them are not important, and some standard deviation. So some of them do have values, some can even have a large value depending on sigma square. And in that case, the likelihood function is a map function. And now, rather than maximizing the likelihood of y given x, we maximize the likelihood of y given y and theta, which is basically, right? I mean, based on the chain rule, is the probability of y given x theta, which we did already, times the probability of theta. And the probability of theta now is basically, if you take the log function and sigma square, right? And sigma square we take out because it's fixed, we don't care about it. Basically, it becomes Wj square over 2 sigma square. Okay, everything else drops out, and this is the log, so e to the power of minus, so this becomes a minus of this. Okay, so this is now a new log likelihood function. Again, we still cannot solve it in a closed form solution, but we can iterate and find the best solution, but now take into account not just the derivative for this one, but the derivative for the entire function. So if this is positive, we go up. If this is negative, we go down. But when I say this, I mean that we take into account the prior that we had as well. Okay, so this is called regularization. And again, this is using some probabilistic assumption that basically leads to a map estimate. In the problem set, you will use other regularization that has the same motivation. So the motivation is that we don't want to have very large value for parameters for most features, because we think most features are not that important. So we want to have most features be close to 0. So one way to do it is to minimize the least square, or the square value with some function of the variance. Another is to minimize the absolute value. So this is called L2 regularization, because we are maximizing the square of the parameters. And absolute is called L1, because we're minimizing in the absolute. And it's actually a bit harder to do, so we leave it to the problem set rather than doing it in class, which is fair, I'm sure, right? Okay, good. So this is basically the new update rule. So the only difference is that we still do the gradient descent and we still move slowly, but now we take into account not just the function, but also the prior that we had on the. Okay, so this is the map estimate, as I mentioned. And as I said, there are other ways to do regularization. I mean, the most common ones are L2 and L1, honestly. So L1, usually also known as, or sometimes known as lasso for logistic regression, and L2, which is the standard one. Okay, good. So this is mainly it for logistic regression. This is what you will need for the problem set. We are still missing one last point, which is for, the fact that logistic regression can be applied to multiple classes. It's really a small point, so I will mention it at the beginning. We're out of time, so I will discuss it at the beginning of the next lecture. Problem set 1 is due today. So don't forget, everybody who is not, and problem set 2 is also going to be released, I guess, later today or early tomorrow, Daniel?
Should be released pretty soon.
Okay, so later today we should.
Yeah.
Okay, and I'll see. Oh, one very important thing. So we are Wednesday. There is no class. I should have mentioned it at the beginning. Hopefully people didn't leave. There is no class on Monday. So Monday is the holiest Jewish holiday of the year. So I'm usually taking it off. And there's not going to be a class on Monday, so we will meet again on Wednesday. Okay, so we will, and next time we are talking about support vector machine, but there's no class on Monday. Okay, and so we'll see everybody next week.